Hi class. We are covering chapter 10, and in chapter 10 is drawing Lewis structures. Chapter 10, 10.2 gives you guidelines how to draw Lewis structures. I learned a different way that for me is easier than what most books tend to cover. The way that I learned was not when I was a student, was after I was a student, of course. And most chemistry books do not show the way that I know how to do it. I don't know why, because I learned this when I got like done with this portion of chemistry, so it's been around forever. But most books that I deal with don't show this. So I'm going to show you a way to do it. It's not foolproof. There are, problems with it. Certain elements and atoms don't fall within the guidelines to use it, but we'll cover that right now. So your book shows you one way, and it is on page 446. I definitely suggest you read it because that way might make more sense to you than the way that I do it. But my way is not foolproof. It does not work for every atom Lewis structure that you want to put together. Why? Because when you start getting into higher energy levels, it can't account for them. So when you start dealing with anything past n, it basically works well for anything in n equals 2. So up to 2p, which doesn't sound like a lot, but most of the elements that you learn for Lewis structure until you start getting to really complicated stuff, they all pretty much cover n equals 2. So for the most part, they will cover a lot. Once you start getting to n equals 3, you can use it. It can give you a suggestion, but the compound or the Lewis structure you put together may not be completely right, but it could help you in a sense to put something together, and then you figure it out from there. Also, if it's a resonance structure, which is covered in 10.3, you may be drawing only one structure and you still have to figure out what the other ones are. So basically, like everything in chemistry, it's not always clear cut. There are exceptions to the rule, but for the most part, it's a guidance or suggestion that can help you with your stuff. Okay, so I have put together some problems and they're straight from your book. So I have put the page numbers next to them. So I definitely suggest you read the way the book tells you to do it. So you know that way, and then read how I do it. My way is limited. It only goes up to a certain point, where the guidelines for the book pretty much covers just general across the board. So here are the steps, and then probably won't make sense, but once I do the problems, it will be clearer for you. Total amount of electrons. This means valence electrons. I forgot to put that up here, but we don't ever work with core electrons. So when we're discussing Lewis structures, it's valence electrons. If you have, you're given atoms and you have to put it together, you account for all the valence electrons for each atom for number one. Number two, the amount of electrons needed for each atom. Now this is very simple, but it's also very confusing for students. The answer here is either 2 or 8. There is no other answer for each atom. So for instance, if I have an oxygen in number 1, I have 6 valence electrons. But for 2, I have 8. I call number 1 what I have to work with, and number 2 is what I need. So for number 2, I need an octet. So the answer for that atom is 8. But I only have for number 1, 6. And if this doesn't make sense, it will when I do problems. You account for the total amount for each one. It's either 2 or 8 for each atom you're working with, just like you total the valence electrons for number 1. Number 3, you're going to subtract 2 from 1. These are the electrons you have to work with. Then for number 4, you're going to divide that number from 3 by 2. Why? Because 2 electrons are for a single bond. This is going to tell you how many bonds you have to work with within a Lewis structure. Number 5, determine the central atom. Try to keep the structure as symmetrical as possible. In most cases, the symmetrical atom is structure is the lowest energy. When you start dealing with resonance, you will deal with several structures, but the symmetrical one, 99% of the time, is usually the lowest energy one. In most cases, not always, like again with chemistry, but for now, keep that in mind, in the back of your mind when you're doing these. And hydrogen is never a central atom. Surround the central atom with the remainder atoms and try to keep them as symmetrical as possible. Number 6, subtract 3 from 1. Once you have put the bonds out there, you need to determine your lone pairs. So you're going to subtract 3 from 1, and that's going to give you the remainder of electrons that are left, and you put them around the atoms that can support that to make an octet for each. And if you have a resonance structure, you're going to need to determine the other structures, but this could help you get started with that. Periodic table, I put in a periodic table here to help you. Also valence electrons, I found this online. Again, something general to help you understand this. That's why it's blurry, because I found it online. I found all these online. And then electronegativity will also come to play when you're trying to determine a central atom. The way that I learned it is the least electronegative, the least, not the strongest, is usually the central atom. Usually, again, not always, but is usually the central. In most cases, carbon, if you have a carbon and an oxygen, carbon tends to be the central. It is lower value of electronegativity than oxygen. Oxygen is the second most electronegative atom. All right, so I put the page numbers here so that you can see which problem I'm working on, and you can compare how the book did it versus how I did it. There is no right way. Whatever way works for you is the way you should do it. Okay, so one thing you guys should know, I bought this drawing tablet for this course. I'm learning how to use it, so my writing looks sort of chicken scratch, and I apologize. I do my best, but I'm still learning. And it's red, and I don't even know how to change that. So number one is what we have. So I tend to nickname this have, like I said, I'm still, when you watch YouTube videos, you see people write so nice. I'm barely learning. It's like riding a bike for me. All right. I set them up with what I've been given here. This is what I have to work with. So 4 valence electrons for carbon, 1 for hydrogen, and then here I have 3 times 7. You guys should be fairly comfortable with understanding where valence electrons for elements are for each. So this is 21, 21, 22. So I have 26 valence electrons to work with. Number 2, I label this my need, and I just simply copy the same thing over again. All right. And this is an answer of 2 or 8. So I need 8 to make an octet. I need 2 for a duet. And I have 3 times 8 is 24. So the answer here is 34. Okay. Now, number 3 is to subtract them. So 34 minus 26 is 8 valence electrons. And then number 4 is divide by 2. Why? Because 2 electrons equals 1 bond, a single bond. Okay, so I'm simply going to come back here. I'm going to divide 1 bond, and this equals 4 bonds. Okay, so I'm going to draw it here, draw it in the center. So 99% of the time, carbon tends to be the central atom. Hydrogen can never be, because it can only take 1 more electron. And chlorine, in this case, there's too many. You couldn't keep it symmetrical. So we're going to make carbon our center, and then you try to keep it as symmetrical as possible. And there's really not a way to determine where the H goes, because there's 3. So chlorines, we're just going to leave it like that. Okay, so that's my 4 bonds here. I'm going to plug these in. 1, 2, 3, 4. And I skipped a spot, a point. Is that my cat? Sorry. You are going to determine, I don't know if you guys can hear my cat meowing. Determine, I jumped ahead and I apologize, the central atom. And then the surrounding. So in this case, carbon is the central atom. I've learned it because it is the least electronegative over carbon. Hydrogen is never counted. So it's strictly between carbon and chlorine. And so, and the surrounding atoms. So let's write and. Again, my writing on this thing is, I already don't have nice writing. And this just highlights how bad it is. I'm left-handed and this thing makes me write kind of weird on it. Okay, so now we need to, we're not done. We need to finish this. So number 6 is to determine your lone pairs. So we are going to take number 3 and we are going to, which is this number here is the one we're interested in. We're going to take number 3 and subtract it from number 1, which is what we have to work with. So we have 18 valence electrons to work with. So now we just start putting them out. 1, 2, 3, 4, 5, 6. I do a little housekeeping here to make sure that I am on track. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now we just check it. So a hydrogen needs a duet. So 1, 2, that's fine. And everything else here should be 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Sorry if you hear noise, my cat's just going crazy. Wants my attention. So this is, as far as I put it together, is correct. So you can match it with what you did in the book, of what the book does, and see which one works for you. Okay? So now we're going to do it again. And the steps never change. So the nice thing about this is, there's my cat. The steps, she's just acting up right when I've got to work. The steps never change. Okay, so now we're going to do it again. Same thing. Nothing changes here. So this is what I call my have. So CHO2. So we have 4 times 1, well, 2 of hydrogen. Sorry, I'm working it out now, speaking it. We have 4 valence electrons for carbon. We have 2 hydrogens, so you have to count for that. And then we have 1 oxygen. So we have, this is 6 and 6. We have 12 valence electrons for this compound to work with. Number 2, this is what I call the need. So again, copy it over the same way. I need to fill an octet for carbon, so it's 8. For hydrogen, it is a duet, so it's 2 times 2 equals 4. A duet is 2. And then for oxygen, I need 8. So this is 20. I need 20 valence electrons to fill an octet. So this already tells me I don't have enough. Something's going to have to be done here to make this fit. Number 3, subtract them. So 20 minus 12 equals 8 valence electrons. So I have 8 valence electrons that need to be shared within this compound to fill an octet. Number 4 is divide by 2. So we're going to divide by 2. This tells me 4 bonds again. A bond. Put it like that. All right, number 5, the part I skipped is pick central atom and surrounding atoms. So carbon's it. Carbon tends to always be it in most cases. I don't want to always say always. 99% of the time. There's my disclaimer. Now I have 2 hydrogens and I have an oxygen. So I'm going to put my oxygen up here and I'm going to put my hydrogen here and my hydrogen here. But honestly, it really doesn't matter. Doesn't matter how which way you flip this. It's going to be the same, just like the previous one. All right, I have 4 bonds. So I'm going to plug them in. Hydrogen can only have 1 bond. It will never change. So if you guys are noticing, I have 2 bonds. I use 2 bonds. That means I still have 2 bonds left. Having 2 bonds left means that they have to go on the oxygen, which makes sense because when you start dealing with resonance, you're going to start discovering that some atoms can hold more bonds than others. So carbon, oxygen, nitrogen, those tend to, they can hold up to triple bonds, and some others. Phosphorus, sulfur are others that can hold more than a single bond, and they all tend to be together on the periodic table. So when you're dealing with carbon and oxygen, they definitely can hold up to triple bonds. So this makes sense that that's where the bond's going to go. Okay, but we're not done because we need to place the remainder valence electrons for the lone pair. So we're going to take number 1, our 12 valence electrons, and we're going to subtract number 3. This is what we have left for lone pairs. We need to put these on here. So hydrogen can't take any more, either hydrogen. Carbon, if you already count it, is 2, 4, 6, 8. It's already got an octet. We can't add it there. So the only thing that can do is put it on the oxygen. And when you have a double bonded oxygen, the electron pairs tend to go on the sides. So I call them like little ears. You put them on the side of the oxygen. So I just put 2 and 4 down. So minus 4 is 0. So I used them all. Let's check the compound. So this is a 2. We're good. This is a 2. We're good. This is 2, 4, 6, 8. We're good. So let's see. 2, 4, 6, 8, 10, 12. We worked this compound out and it looks correct the way that it should be. So again, we got another one done. Now, let's go on to the next one. So we now have 2 carbons and 2 hydrogens. So let's put this together. So number 1 is my have. I suggest if you guys are able to, well, you should be. Pause this, work it out yourselves, and then see if it matches. So 2 carbons, 4 hydrogens. Let's see what we have here. So I have 2 times 4, and I have 4 times 1. So this is 8, and this is 4. So I have 12 valence electrons to work with. I call this my need. Copy it again the same way. So 2 times 8, and then 4 times 2. Remember, it's a duet. We want to fill this as either always a 2 or an 8. Never changes. Don't make it harder on yourselves. Those are the only values you can give here. And then this is 8. So this is 24 valence electrons. Again, we're going to be short here because these numbers are not matching. Number 3, 24 minus 12 is 12 valence electrons. So this is what we have to work with. So number 4, divide by 2. So let's divide it by 2. So we're going to divide it. Let's do bond. And this is going to give me 6 bonds. Okay. Number 5, determine central atom and surrounding atom. All right, so let's put this together. We have 2 carbons now, so it makes it a little interesting. So let's put 1 carbon down and another carbon. All right. Now, I can tell you right now, we have 2 here and we have 4. So I'm going to start spreading these. Remember, it's got to be symmetrical. So I'm going to share these hydrogens between these carbons. So I'm going to put 1. Oh, I already put that there. Sorry, and I don't know how to delete it. Okay, so we'll count that right now. All right. Why did I put them side by side like this? Because I don't want to put another carbon and then hydrogen. I make 1 carbon the center because it wouldn't be a right. It's not going to be a correct the way it's going to look. And honestly, it's not going to matter. Once I put this together, you'll see. So I have 6 bonds. I don't want to get ahead of myself and then confuse you and myself. 6 bonds, which one I already put down. So let's put the others. I have 5, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. But I have a problem because I have 1 bond left. I told you carbon can handle this though. So we're going to put it right there. All right. So I have actually taken care of. If I ever try to put it with the hydrogen, I'm violating the rules. It's not going to work. It's an unstable compound. It wouldn't exist. And if it did, it wouldn't exist for very long. So carbon can handle the double bond. So that works. Now we need to determine if we have any lone pairs. So I have 12 here, right? And I have 12 here. I have 0. I have no lone pairs. So I am done. Let's check. 2, 4, duet. That's 2. That's a duet. That's a duet. And now let's check each carbon. So when you do a carbon, look at one carbon only, and then look at the other one. So 2, 4, 6, 8, that works. 2, 4, 6, 8, that works. And if you needed to check just to make sure, count them all. 2, 4, 6, 8, 10, 12, done. This compound is done. And it should match, it should work, because if it didn't, it would violate it somehow. All right. And then our last one is an ion. So we are going to take care of this one. It's on page 451. You can actually do ions on here as well. So we have our number 1, which is our have. Just one step here is different, and if you don't do this step, you will have problems. All right, so I have a carbon, which is 4. I have 3 oxygens, so 3 times 6, and now I got to count for the 2 charge. I'm going to put, I put a C here, a CH charge, one right there, and a 2. This is the only difference in the step. You have to account for the charge in number 1, and that's it. And then, of course, you have to draw it out with the charge on it. If you don't, then it's wrong. All right, so we have 18. We have here, 18, 22, 20, 20, 24, 24. Is that right? Yeah, 24. 24 valence electrons. All right, number 2, we're going to copy it over minus the charge. That's the only place that the charge is going to show up. So I want 8, and I want 3 times 8 equals 24. So this is 24, this is 32 valence electrons. Again, there's a discrepancy. It's not going to match together. We're going to have to share some electrons. So 32 minus 24 is 8 valence electrons. It seems to be a popular number. And number 4 is divide by 2. So we're going to divide by 2. 4 bonds. Number 5, pick central atom. Sorry, I don't know how to erase anything on here. So once I make a mistake, it's there forever. And surrounding. By the way, I just learned that I could write on my PowerPoints last week, so that's how new this is for me. The student that was in there with student session, he knows who it was. You would have thought I won a car. I was so happy to figure this out. All right, so pick a central atom. Carbon is going to go there. And then what I'm going to do is I'm going to put an oxygen there, and an oxygen, kind of in a triangle. Tends to work better. Okay, so I got 4 bonds. Let's do the 4 bonds. 1, 2, 3. Now I'm stuck. I have 1 bond left. Where do I put it since I have equivalent oxygens? Well, this is where resonance come in. And I'm not going to go into resonance here because that will be another lecture that I should be putting up for you. This, I'm just going to pick one. I'm going to put it, oh no, I'm going to put it here. It'll take it. Okay, I'm going to put it there. But all of these are equivalent, and we'll cover that right now real quickly. All right, so I have 4 bonds. I covered it. This is for this one. So number 6 is determine my lone pairs. All right, so I'm going to take my 24, and I'm going to subtract 8 from it. These are valence electrons. So I have 16 valence electrons left, so let's plug them in. All right, so first things, I like to get done with compounds before I jump to other ones. So I'm going to put my little ears on my oxygen here. When it's a double bond, where do I do that? When it's a double bond, it has little ears, so that's 4. All right, and now let's take this one. I have 2, 2, 4, 6, 8. I put 6 down. And then 2, 4, 6. Am I done? If you said yes, this will be wrong. Why would it be wrong? Because I have a charge that I need to account for. And if you don't put that down, then you're just making this a regular compound, which it is not. So you have to do these nice little brackets, these lovely little brackets, and put a 2 minus. Now, this is where resonance comes in. I should have drawn this smaller. I know it's not the greatest. And if I learned how to erase, I could make this nicer. Hold on, let me draw this, and then I will explain. Put the ears. Hopefully that sticks for somebody. Oh, I forgot to put the ears. All right, and then we have one more on this side, and this is the worst side for me to write. Okay. You can see, put the ears. I should put the ears first. Take care of this one. This is resonance. Some compounds, one structure does not show the exact bonding that goes on. So you have to draw other structures to basically show it's a combination of several structures to show what the bonding is. Why? Because double bond is not on one oxygen. It kind of moves and shifts between these. And what it kind of looks like, if I can draw this, but of course, this isn't going to be what you would need to draw, is what they have found is that there's kind of a in between a double bond and a single bond is what it looks like, but that doesn't really make sense. So you have to draw them out like this. And the arrows means that the bonding, the energy of these structures moves between the oxygens, and you have to show that on here. So this is a complete resonance structure for this, these three structures. Your chapter, there is a chapter in 10.3 that covers resonance, and this is actually covered in this Lewis structure is covered on 451. So you can compare how they did it versus the way I did it. Now, the way that I do it only draws one structure. You're going to have to draw the others. How would you know? Sometimes you just have to get familiar with the way that certain elements are, and if they are symmetrical like this with a double bond, you got to account for that energy being moved to the other ones, because if you don't, and you draw one structure, you're saying that the one structure, let's say the first one, is the only structure that exists, and it's only on one oxygen that has the double bonds, which isn't true because it's truly symmetrical. That's going to be shared, and you have to show that that moves around on here. So hopefully, these are the problems that I did. I took them straight from the book, so you can compare. For some, I hope this makes your life a lot easier trying to understand this. Again, it's doesn't work all the way. Like for this one, you need to know by reading that chapter that, and what I'm just explaining to you right now, you're going to have to show the resonance on this. You're going to have to show the oxygens are account for all the energy on all the oxygens, and look for things like this. Okay. And if you have any questions, you can always contact me.